Welcome to this explainer. Today, we're diving right into the absolute magic and hard science of aircraft propulsion. We're going to break down the mechanics that make flight possible, looking strictly at the technical documentation and the physics that aviation engineers use every single day. Here is our roadmap for today. 1. The secret to thrust. 2. Turbojets versus turbofans. 3. Calculating engine power. 4. The quest for efficiency. And 5. The ultimate balancing act. Section 1. The secret to thrust. Let's bust a major myth. Before we even touch a turbine, we've got to tackle the most fundamental problem of flight. How do we actually move forward? Now, you might be wondering, does an aircraft just push against the air behind it? It's a super common misconception. A lot of us picture an engine working kind of like a swimmer, pushing off a pool wall. But looking at the source material, that is simply not true. The real answer? It all comes down to Newton's third law of motion. For every action, there's an equal and opposite reaction. The engineering manuals spell this out clearly. Propulsive force isn't about pushing on the outside air. Actually, it's all about displacing a working fluid. Basically, the engine sucks in air, accelerates it, and blasts it out the back, in the exact opposite direction the plane needs to go. That blast of air goes backward, and the reaction? That pushes the engine and the whole plane forward. And this brings up a really fascinating comparison. Both aircraft and space rockets rely on this exact same Newtonian principle of displacing mass, but they get that mass in totally different ways. See, an aircraft uses the atmospheric air around it as its main working fluid, but out in the vacuum of space, zero air. So a rocket actually has to carry its own oxidizer for combustion. It relies entirely on accelerating and displacing its own total combustion gases to get that equal and opposite reaction. Moving on to Section 2, turbojets versus turbofans. Let's look at some engineering solutions. So how do engineers actually apply this law using completely different types of engines? Now, what's really interesting here is the contrasting mechanical approach to displacing that fluid. You can essentially get the exact same amount of thrust in two very different ways. On one hand, you have turboprops and turbofans. They generate thrust by grabbing a massive amount of air and accelerating it relatively slowly. But on the other hand, turbojets take a much smaller chunk of air, but they accelerate it through a massive, rapid velocity change. The technical notes show us that a turbojet passes literally all of its gases directly through the core of the engine. But turbofans and turboprops, they're a bit different. They use the mechanical energy generated inside the engine to turn a huge fan or propeller. And that fan moves a colossal amount of air that never even touches the engine core itself. It is just such an elegant solution for maximizing thrust. All right, Section 3, calculating engine power. Time to measure the muscle. Now that we know how thrust is actually generated, how do we measure the raw muscle of these massive engineering marvels? Well, you're probably used to normal car engines, which are rated in brake horsepower, but we can't measure the useful output of a gas turbine the exact same way. Since gas turbines generate a forward push instead of just turning a shaft, their output is rated in thrust horsepower, or THP. And to convert that thrust into a horsepower rating, engineers use a very specific magic constant, 375. So where does that number come from? Well, one standard horsepower equals 33,000 foot-pounds per minute. Multiply that by 60 minutes and you get almost 2 million. 1,980,000 foot-pounds per hour, to be exact. Divide that by the 5,280 feet in a mile, and boom, you get exactly 375 mile-pounds per hour. This number is literally the bridge between raw thrust and horsepower. Okay, let's dive into this actual mathematical formula pulled straight from the manuals. The formula for thrust horsepower is surprisingly simple. It's just the thrust multiplied by the aircraft's speed in miles per hour, and then you divide that whole thing by that magic constant we just talked about, 375. Let's walk through an example step by step, just to prove how totally accessible this math is. Step 1, let's say our turbine is pumping out 4,000 pounds of thrust. Step 2, the aircraft is cruising at 500 miles per hour. Step 3, we multiply 4,000 by 500, which gives us 2 million, and then we divide that by 375. Step 4, the result is 5,333.33 thrust horsepower. And you know what's wild about this? Varying the speed of the aircraft directly changes the horsepower calculation, even if the engine's raw thrust doesn't change at all. On to Section 4, the quest for efficiency, fuel and speed. But hey, raw power is only half the equation, right? For these engines to be practically viable, they absolutely must be economical when it comes to fuel. The baseline parameter engineers use for this is called thrust-specific fuel consumption. Basically, it's the fuel flow measured in pounds per hour divided by the thrust in pounds. This metric is absolutely crucial because it lets engineers make direct apples-to-apples comparisons between the fuel efficiency of completely different types of engines. When you apply this to real-world flight planning, you hit a critical performance barrier. At lower speeds, reciprocating and turboprop engines have vastly superior fuel economy compared to pure turbojets or turbofans. But there is a catch. The source text outlines that once you push past 400 miles per hour, a turboprop's propeller starts losing a ton of efficiency. So at those high speeds over 400 mph, the turbofan steps up as the undisputed champion of efficiency. And finally, Section 5, the ultimate balancing act: safety, cost, and design.
Because let's be real, raw power and brilliant fuel efficiency mean absolutely nothing if an engine breaks down mid-flight. When we evaluate engines, we hear the words reliability and durability tossed around like they're the exact same thing. But as the documentation clarifies, they aren't. Reliability is an engine's ability to perform at its specified ratings in extreme weather and crazy flight attitudes. Durability, though, is the engine life you get while maintaining that reliability. And this brilliantly illustrates a core manufacturer goal. An engine has to perform safely today, for sure, but it also has to keep doing it over the long haul.
So the big question becomes, exactly how long can that engine safely operate before it needs a total teardown? That's known as TBO, or time between overhauls. And TBO is highly variable. It's dictated by some pretty extreme operating conditions: how hot the engine runs, how much time it spends maxed out at high power settings, the quality of maintenance it receives, and strict adherence to limits during pre-flight inspections. Paying careful attention to all these factors is exactly why engine failure is incredibly rare today. Finally, we've got to talk about the physical constraints of the aircraft itself. The source material heavily emphasizes the absolute necessity of compactness. The engine's shape and size must be as tight as possible. Why? Because a huge frontal area creates a massive amount of aerodynamic drag. And elongated, spread-out designs, they make it incredibly tough to keep the engine's weight within safe limits. Literally every inch and every pound matters up in the sky. Which leaves us with a truly provocative engineering contradiction to wrap things up. If maximizing efficiency and thrust means we need a larger fan to push more air, but minimizing drag and weight means we need the most compact engine possible, how on earth will engineers resolve this? What is the highly efficient aircraft engine of the future actually going to look like? It's a puzzle that is pushing the absolute boundaries of modern physics and manufacturing. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.